This morning we're going to be talking about our second gas law, Charles's law. So Charles's law explains what happens to a gas when we heat it up. So the way that we want to think about this particular law is actually in terms of hot air balloons. And I don't know if any of you guys have ever ridden in a hot air balloon before. I haven't, but I have a drawing of a hot air balloon here behind me. And if you've ever seen one at the beginning, before they take off, the hot air balloon is like slumped on the side. It's like all laid out, but it's kind of sitting on the ground. And they fire up this big oven, this big stove kind of burner. And what starts to happen is it heats up the gas that's trapped inside of the bag. I mean, I don't know if this has ever occurred to you before, but a hot air balloon is only full of the same exact air that you're floating in. So how do they do that? So as they start to heat up the air in the balloon, the gas gains kinetic energy. And we know kinetic energy is the energy of motion. And as it starts to gain kinetic energy, those gas particles start to spread out. As they spread out, they become less dense than the air around them. And so by heating the air, you actually make the gas that was just flat in the bag. You make that gas gain so much energy that it inflates the balloon. And then the balloon, the air that's in this balloon is less dense than the air around it, so much less dense that it can raise not only the basket, but the people inside of the basket. So as you go up into the air, you are riding on just warmer air, exact same air, just warmer. And if you turn off the burner, then the air loses its kinetic energy and the gas particles start to condense again. And they continue to condense and the balloon starts to slowly drift down to the ground. So Charles's law tells us that as you increase the temperature of a gas, the volume, the size of the gas also increases. Almost always when we talk about Charles' law, we are going to be in a balloon or in a tire, which is a really good thing to think about when you are trying to figure out which kind of question are you answering. If you're in a balloon or a tire, there's a very good chance that we're talking about Charles's law. So on one hand, our gas, as it gains energy, as it gains kinetic energy, expands. But if you go the other direction, you think about it the other way. If I cool that hot air balloon down to room temperature, it lands on the ground and the balloon falls back over and is flat. But if I keep cooling it, if I bring the temperature down lower and lower and lower and lower, eventually those gas particles get so cold that they form a liquid and then they form a solid. And then as I keep cooling them and cooling them and cooling them, the idea is that their movement should eventually completely stop. So when we graph that, this is our graph here. When we graph gases like helium and methane, water, and hydrogen, and we graph what happens as we lower their temperature, they get a smaller and smaller volume. This is the volume over here. This is how much space they take up. So as we decrease the temperature, we cool and cool the temperature, the volume drops down. But a really interesting thing happens. No matter what gas we look at, the temperature cools and has the exact same x-intercept. I'm sorry to use math words on you, but this x-intercept here is where the line crashes in to the x-intercept. And so what happens, what we see is with water, with helium, as you cool them, they actually, if you look at their trajectory, are going to crash into the x-intercept at the exact same point. And I know you guys know this from math, but you can actually calculate what number they'll crash into the x-intercept. And it turns out that they crash into the x-intercept at negative 273 degrees Celsius. So just about every gas, or really every gas that we can graph like this, will extend its line to be zero volume at to negative 273 degrees Celsius. And so a man, Lord Kelvin, like lords and ladies, Lord Kelvin, took advantage of this and he started a third temperature scale. He took this 273 temperature and he called this negative 273 Celsius, he called that zero. We call it absolute zero, the lowest temperature possible. We can't even reach absolute zero. We're not even good enough to get there. And if we could, we wouldn't be able to measure it because by the time we got to absolute zero, all of our instruments would stop working. They would stop being able to take temperature. It's this really kind of hypothetical thing, but we can get close. And so what Lord Kelvin did is he starts this temperature as zero, and he calls that 0 Kelvin. And then he works up in only positive numbers from there. So the temperature that water freezes in our knowledge is 0 Celsius. For him, that would be 273 kelvins already. Okay, so his numbers are pretty high. They're pretty high numbers. But the great news is they're never negative. You've been doing algebra long enough to know that when you throw in a negative number into an algebra equation, it messes up the equation. It makes your equation plus or minus this amount, okay? When we change to the Kelvin scale, we don't need to worry about any negative numbers. And so it actually makes our math a lot easier. So 2 things about Kelvin. One is that it's derived, this Kelvin scale is derived from Charles' law, this idea that temperature and volume are connected. 2, now that we have the Kelvin scale, we are going to use it for every gas law problem, which means to you, you should never plug in a number that's in degrees Celsius. You should only be plugging in things that are in Kelvin. So the lowest temperature possible is negative 273 degrees Celsius. We call it absolute zero. These are all things I've already told you. And so 0 Kelvin is negative 273 degrees Celsius, or 0 degrees Celsius here, which is the temperature water freezes, is positive 273 degree Kelvin. So we need to learn how to exchange between Celsius temperature and Kelvin temperature, because you're going to need to do a lot of that in your math problems. So what we do is pretty simple, actually. Whatever the degree is in Celsius, we're going to add 273 to that to get to Kelvin. So if something is 20 degrees Celsius, if I want to change that to Kelvin, I'm just going to add 273 to get to 293 Kelvin. Now, Kelvin does not have a degree sign with it. It just is 293 Kelvin. If I were going to take my number back, let's say I finished my problem and it said in what temperature in Celsius is the new balloon, okay? And I got an answer out of my problem that was 283 Kelvin. I would then subtract 273 to get 10 degrees Celsius, okay, for my answer. So if you want to go from Celsius to Kelvin, you add 273. If you want to go from Kelvin to Celsius, you subtract 273. So we'll be doing that regularly, kind of at the beginning of each of our problems. Okay, so now that we have figured out how Kelvin temperature works, remember Kelvin temperature was both derived from Charles' law, but also now we use Kelvin temperature every time we do Charles' law. But Charles' law itself just states that the volume of a gas at constant pressure varies directly with the temperature. That means that as we raise the temperature, the volume gets bigger, and as we lower the temperature, the volume gets smaller. This is a direct proportionality, which means that as one goes up, the other goes up. So we're going to look at a graph of volume versus temperature for a gas at constant pressure. So over here we have the volume, and down here we have the temperature. And what we see is that as the temperature rises, the volume also rises. So we get a straight line. Straight lines have a mathematical slope of rise over run, which you've probably heard in your math classes before, that the slope of a line is rise over run. Now that means that the slope of a point right here is the rise divided by the run, okay? Rise over run. So we would do something like 400 divided by 200. So I'm going to just put that back here for a second. Whoop. So we would have the slope of our line that might be something like 400, which is our rise, okay, where we are on our rise. And again, we're looking at this point right here, 400 divided by 200. And we know that 400 divided by 200 should be 2, right? Like 4 divided by 2, right? Yeah, okay, good. Okay, so then if we take another point along here somewhere that would be easy enough to see, if we went up to 400 here, right at this point, we would be 800 would be our rise, and we would be dividing that by 400, which would be our temperature. So 800 divided by 400 also equals 2. So what we've proven here is that our rise over run stays consistent. The slope of the line stays consistent. So instead of setting these equal always to 2, we could set them equal to each other. And that's exactly what Charles' law does. So it sets one rise and run equal to a second rise and run. If you wanted to see this in terms of derivation, what that would look like is it would look like saying, okay, 400 divided by 200 is equal to our other one, 800 divided by, and then this would be what we were trying to find. We would be trying to find the second piece here. And so that's kind of what Charles' law is going to be doing, is we're going to be knowing 3 out of 4 pieces of our volumes and temperatures.